what I want to talk about tonight is a little bit of electronics, and we've talked about electrical applications. But when we talk about electronics, we're talking about devices and applications that really work at the electron level. I mean, all electricity is the flow of electrons. But when we deal with electronics, we're actually controlling electrons sometimes even one at a time. If you recall, we talked about the conventional flow of electricity and the electron flow. We said that in one theory, current leaves the positive and goes around to negative, but really the flow of electrons would be leaving the negative side and flowing the other way. That's the electron flow theory. When we talk about different atoms, we talked about that there were protons in the middle, and then in these outer orbits were the electrons. And we said that whether or not a substance was a conductor, an insulator, depending on how many electrons were in that outer shell, that outer orbit that they call the valence electrons. And if there's 1 to 3, just 1 to 3 in the outer, that makes it a good conductor. But the more electrons you have, the less likely that atom is to give one up. So when you have one out here on an outer orbit, it can get thrown off easily and make it available, which means that makes electron flow easy. But if they're bound tightly to the atom and they're harder to shake loose, that's what makes them an insulator. So semiconductors is what we're going to talk about a good bit tonight. Semiconductors fall in between that. They'll have like 3, 4, or 5 electrons in the outer or valence shell. So they're in between a conductor and a semiconductor. You can see up here in a conductor, many electrons are flowing. In a semiconductor, not as many are flowing. And then in something like glass, porcelain, rubber, you don't see them flowing at all. Now remember that if we increase the voltage, even glass will conduct. So here's a couple of typical substances that they use in semiconductor devices: germanium and silicon. If we look at germanium, it's atomic number 32 because it has 32 protons. It also has 32 electrons, but it has 4 in its valence orbit. Silicon has 14 protons, 14 electrons, again, 4 in the valence or outer shell. If you have a lot of these atoms together, they start to bond. There's this atomic bonding that occurs, and because atoms like to have 8 electrons in their outer shell, they will share the electrons. So here you can see silicons that have 4. Look at this one right here. It has 4 because that's how many it typically has, but when they start joining together, you can see these inner ones essentially have 8. This one has 8 because of the sharing. And because of this bonding together, this starts to form crystals. So silicon crystals are made up of silicon atoms, and they're bonded together by this electron bonding. So when we talk about semiconductor material, there's 2 different types. There's N-type for negative and P-type for positive. If we take something like silicon, is what they've done here, they've taken silicon, and we introduce an impurity to that mix, this process is called doping. And what that does is affect the electrical characteristics of that semiconductor crystal. Here they used, I think this might be arsenic because that's a common one, but arsenic has an extra electron. So when these silicon atoms start to join together, it will still bond with this arsenic atom, but because there's an electron left over, that makes it an N-type because electrons are negative. So the silicon have 4, if we saw. Arsenic has 5 extra electron. And the more of these impurities that you add, the heavier the doping, the more N-type this becomes. So block symbol, It's got little negative signs in it. And if you hook it up like this to a source, it pretty much acts like, now see, they're showing the electron flow, electrons leaving from the negative and going through this way. Nonetheless, if we use the conventional flow theory and say that it's going this way, the light bulb still comes on, so it doesn't really matter. But in any event, this acts not like a short circuit or not like an open circuit, but kind of just like of a resistor, like some sort of a resistor. It will let current go through it, but with some impediment. Now the p-type, now we have a substance and it has an absence of an electron. It only has 3 electrons, so there's a hole there that's left a hole. So we're doping it with a different type of impurity, but because there's a hole there, which is essentially a place to accept an electron or a positive, it's a p-type. Again, the more of this substance we put in, the more heavily doped it is, and the more p-type it becomes. Different symbol. If you put it in a circuit, it pretty much acts the same as the n-type. So whether it's p-type, whether it's n-type, when they're by themselves, they pretty much act like resistors. And because of that, because these are difficult and expensive to make, you've probably seen pictures of Silicon Valley where people are working with these things with like hazmat suits on, because if you get a piece of dust and these crystals, it alters the, when you're dealing with just a few electrons, a few atoms, and then you get a piece of dust in it, that's a significant contamination. So they have to be very careful about that. So it's very expensive to make semiconductor material. And in an application like this, where it essentially acts like a piece of carbon that you can get all over the place, you don't ever use it in this type of an application as a resistor. But here's where you can use it, because if you put a P and an N-type together, it acts uniquely. And we call that a P-N junction diode. And a diode schematic is shown here. You can see we've got a P on one side, N on the other. The anode is the P side that we would normally hook to the positive side. The cathode is the negative side. Conventional current flow goes the direction of the arrow, anode to cathode flow. You might identify a diode. It may have the schematic symbol on the outside. Sometimes they use a band. The band represents this line here. So the current would flow anode to cathode this way. Sometimes they taper the end so it would flow that way. So how do we use this? How do we use this device? A diode only allows flow to occur through it in one direction, the direction of the arrow. So if we hook the P positive to the P side, the anode, then current will flow through that. Pretty much acts like a closed switch. But current can't flow backwards. So if you've ever worked with hydraulics and you've had a check valve, this is what it does. It allows current to flow, but only in one direction. Now, in a reverse bias, the previous configuration was called forward biasing. In a reverse bias configuration, we have it hooked up backwards. So current's trying to flow through the load, but it can't because it's blocked. So in that situation, the diode acts as an open switch. So a diode is short circuit when it's forward biased, and it's open circuit when it's reverse bias. If you want to check to see if a diode's good, if you suspect one's bad, because current flows from anode to cathode, if you have it connected forward biased, the current will leave the meter, because there's a battery in here. The current leaves the meter, goes to the anode, and will flow through the cathode. And this will read pretty much as a short circuit, near 0 ohms. But if you hook it up the other way, now current tries to flow through, but it can't. So it's pretty much acting like an open circuit, and you'll see a very high reading. You'll probably not see overload, but you might. There may be some current. Some current tends to get through, but it's so insignificant that we pretty much consider it an open circuit when it's hooked in reverse bias condition. Also, because you've got a p-type with extra electrons and you have an n-type, or you have an n-type with extra electrons and a p-type with extra holes, when they're up against each other, the electrons move to where there's more on one side of this thing than the other. So one side of the diode has more electrons than the other. Because of that, a voltage is formed, and you can check, and you'll actually read 7/10 of a volt if you check a diode in this way. You'll get an overrange. That's when your meter is put in the diode setting. If you have a diode setting, it'll look like that. Probably one of the most common applications, the use of a diode, is for rectification. Because we have a lot of applications, a lot of loads that cannot run on AC, they have to run on DC. We use a rectifier to convert AC to DC. My input voltage is AC. It's fluctuating direction. It flows one way for half a cycle, and then it stops and reverses the flow direction for the other half. So up here, while the current's flowing positive, it'll be delivered to the load, but as it tries to flow the other way, it's blocked. So this is what you get across the load. Now it varies and it's pulsating because you're only getting half of the wave. This half was blocked. So you're only getting the positive half cycles. It's still considered DC because it's going in one direction. That's the differentiating feature between AC and DC, is whether or not it's going two directions or one. An application here, the load, maybe this is your battery charger. So you've got a battery charger. This is your battery right here. You've got it hooked up positive to negative. And anytime that you're on a positive half cycle, you're pushing electrons into that battery to be stored. Now, if it weren't blocked, it would just suck them back out again on the next half cycle. But because it's pumping these in on every half cycle, that's what charges your battery. It's replenishing your battery with electrons. Here's an example where if I have this switch here and the current is going around the diode, I'm getting full wave to my load. So it's going to have full power available to it. But if I switch, now I'm only getting half of the power that was over here. So essentially it's half the brightness. If it were a motor, we'd say it's half the speed. If it were a heating element, we could assume that it's approximately half the heat because it's getting only half of the available power. Another application would be to protect sensitive devices so that if you plug something in backwards, you don't destroy it. This is something I'm glad they have because I've plugged things in backwards a lot of times or hooked things up backwards. So in this case, if my device says, hey, you need to hook me up positive to negative like this, and I do that, well, then positive comes in, gets through like it's a short circuit, a closed switch, and it works. But if I have it up backwards, then this blocks that flow going through it and it protects it. Here I'm showing a simple power supply, AC to DC power supply. So I've got my source voltage here. Maybe it's plugged into a wall. I've got a transformer and I've got a diode. So I've got full wave AC for my source. And you can see that the diode only conducts on the positive half cycles. Anytime the current's flowing this way, it gets to my load. But anytime it's flowing this way, it's blocked and not showing up at the load. This is another example of the same thing. In this example, it's actually showing the electron flow, but again, the same result. And in this example, Same thing, it's just showing the waveforms kind of side by side as they're occurring on in the same time frames. Again, this process is called rectification. Going back a little bit, we talked about transformers before. I just wanted to throw this back out there. This is kind of an illustration of a transformer. You've got your primary voltage and your primary winding. And here's my secondary winding. I've got a diode and I have a load. So this circuit here is pretty much like the one we just watched as a half wave rectifier. This illustration here shows the primary and secondary windings, but it's also showing as we increase the windings on the secondary voltage rises in correspondence. If the secondary windings are less than the primary, then it's a step down transformer. If they're the same, the transformer is at unity. And if the secondary windings are more than the primary, it's a step up. This illustration, this animation shows the current. It's actually showing it, the current reversing in the windings. Here's my primary on this one. And if you recall, we talked about the magnetic lines of flux that are formed by anything, but in this case by conductors carrying current. The magnetic lines of flux, if you recall, don't really like to go through air. They like to go through metal. So these lines of flux, instead of jumping across this gap to the secondary, we get those magnetic lines of flux over to the secondary by going through these laminated steel plates. So if you ever looked at a transformer, it's going to look a lot like this with these laminated steel plates here to allow the flux to travel through here. This becomes magnetized, and that magnetization causes the induction in the secondary. We talked about half-wave rectification, but that's okay for a battery charger, but it's not okay for everything. Let's say that you were using, let's say a router, like you're going to route the edge of a desktop, tabletop. If I've got some sort of a half-wave rectifier, my power is going to be delivered in these pulses, like poof, 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 and you're going to see that in your work. So to make things a little smoother, a more uniform and a smoother delivery of power, if we can use both half cycles, that'll provide that. So we use a full wave rectifier to do that. And the way this works, if my current's flowing this way, for the first half cycle, can't go this way because it's blocked, but it can go this way. It can't go this way because it's blocked. So its only choice is to go from here down, around, and back to the source. But if it's flowing the other direction, for the other half cycle, can't go that way, so it has to go this way. Can't go that way. So again, even on this half cycle, it's still going from top to bottom and back around. This way I'm going to get both half cycles. It's a different way of wiring it up using grounds instead of coming back to the windings, but it's still going to be pretty much this. When I have these symbols like this for ground, whatever we've used for a common point, these are connected. These are at the same point. That's why they're called common. So these are essentially, you can imagine these being the same point. So if this is, the switch is closed, got current flowing through this way, it's fused, and the lines of flux cause secondary induction. Is this a step up or step down transformer?
Step down.
And you can tell that how?
By the number of coils on the primary to the ratio on the number of coils on the secondary.
That's right. So there's less coils over here. The higher voltage is always on the side with a higher number of windings. So if the current is flowing this way, Can't come that way. It has to go this way, top to bottom, down the ground, which is essentially this same point here. And I've got a loop. And the same thing happens the other direction. This is just an animation that's kind of showing the same thing. But we pretty much, they put the load right in this. This is called a bridge rectifier, by the way, a bridge full wave rectifier. Here they put the load just right in the middle, but the current's still passing the same way. All right, so now we're going to look at some different types of power supplies. Typically, you're going to see a device that has an internal battery. Good example is your phone. So the power's coming from the battery in your phone, but you can use an external battery eliminator. Another example, so they'll also can work as chargers, right? So notice I've got 120 volts AC coming in, and I've got 9 volts DC coming out. For that to happen, what has to be inside of here that we've talked about?
Rectifier.
A rectifier converts AC to DC. And what else?
Transformer.
Step down transformer. Good. Thank you. So block diagram. So I've got an AC supply, it's fused. Transformer's usually going to step down. Got a rectifier that converts it to DC. I've got a filter. We'll talk a little more about filters, but essentially filters take some of the pulsating out of it, those little peaks of those hills, and kind of smooths that out. So it's a smoother delivery. A regulator is usually a semiconductor device that maintains a constant voltage. A lot of times your house current can vary. If you could measure it one day and read 105 volts, you might read it another day it says 125. And that can happen at any instant. A voltage reg, because any chain rise and fall in the AC is also going to be introduced to the primary windings, passed to the secondary. So to keep that fluctuation from occurring on the output, this kind of puts a ceiling on your voltage to keep it constant. So here I'm showing a step down transformer. It's just a little bit of a review. I've got 12 volts, 120, and 12 volts over here. Can anybody tell me the transformation ratio of this?
10 to 1.
10 to 1, good, thanks. So the transformation ratio is 10 to 1. I've got 20 amps over here. Notice I have 2 here. So my voltage, and we said this, the power's the same on the primaries and the secondaries, theoretically, of transformers. And so I have 120 volts over here. This goes down by 10, but the current went up by 10 also. So when I multiply volts times amps for power, I get 240 on the secondary. When I multiply amps times volts on the primary, also get 240. Here's a step-up transformer. Same thing, except the voltage is going up by 5 and the current goes down by 5, so that the power is the same on both sides. Isolation transformer is used for a couple reasons. In this case, it isolates the ground from the circuit. So if I've got a short over here and this person is grounded, and because this circuit also is grounded, like your household current, somebody on the secondary side, there's no link to ground. The load is operating without the necessity of a ground connection. So if you touch any of these conductors, there's no pathway here that can exist. So it's for safety. Another thing that they can use this for is this magnetic core that transfers the magnetic flux from the primary to the secondary. It can become saturated to where it just can't allow any more to flow through it. And if we design an amp specifically for that purpose, so that when it's operating at max saturation, then if I get a spike like lightning, or somebody kicks on a motor that would cause a little spike in the line, it can't get transmitted to the secondary because this is already passing all the voltage that it can pass. Any excess voltage it just can't, it's clamped. A center tap transformer, essentially you take your secondary winding and you put a point. This is pretty much like what we talked about that's outside of your house. So you've got, outside of your house, you've got like, maybe we'll say 1400. You've got that many coming into that transformer out on a pole, but it's a center tapped transformer, so you have 3 wires coming into your house. From A to C, you would have 120, and from C to B, you would have 120, but from A to B, you would have 240. So this would be what you would be seeing in your pole transformer for residential power. Another thing you can do is you can have this tap. So let's say this 120 volts from here to here. This is a secondary. I can tap off of this thing. So like right now, I would be getting 60 volts. And as I raise this up and I'm getting more and more of the winding, it's like changing the length of your secondary winding. You're going to get more and more voltage. So I can have this adjustable to vary this output. Probably a good example that I can think of are in our labs, we have those power supplies that have the dials on them to adjust the voltage. What's inside of that is what a transformer like this that's actually changing the position of a tap on the secondary winding to adjust the available voltage. This is the bridge rectifier that we talked about for full wave rectification. The schematic symbol is that. It might look like this, or it might look like that if it's prepackaged. You see that you hook up the AC to 2 of the leads and your DC come out on a couple of the leads. You know, in your computers are a good example. Most of the stuff that's in there is semiconductors, and most semiconductors operate on DC circuits and power. So you don't have DC available to you, so you've got to take the AC coming out of the wall and provide the appropriate powers for the different devices in your PC. So your power supply will actually have transformers with multiple taps, so that you're going to come out with 5 volts, you're going to come out with 12 volts, because different things in your computer require different voltages. And most of those have to have DC voltages and DC current. So there's also going to be rectifier circuits, diodes, for each of those 2, diodes, filters, and regulators. Just a little bit about 3-phase. We've talked about single phase, this is what comes into our house, but industrial applications have 3-phase power. With 3-phase power, you'll get a wave, you'll get another wave that comes after that, 120 degrees, and then you'll get another one at another 120 degrees. So you'll have 3 waves, 3 windings, basically 3 secondaries. And if I have 3-phase power coming in, I'm going to rectify all 3. This is pretty much like your alternator on your car. Your alternator produces 3-phase power usually, and you're going to have the rectifier that's in it and a voltage regulator. That regulator will be in there too, all those semiconductors, so that the AC that's being created by the alternator, it's called an alternator because the current's alternating, but it's rectified because your car system is DC. This pretty much shows that. And if you've ever looked at the electrical system schematic, you're probably going to see this symbol. Here we're charging up the battery. Okay, so here's a picture of 3-phase power. If you have a rectified power, you're going to have these peaks, and it's these peaks we're trying to get rid of with filtering, which we'll talk a little more about in just a little bit, like right now. What we're going to use is a capacitor, and a capacitor acts like a storage tank, and I'll try to use an analogy that makes sense. Think of this as a storage tank that holds water, and think about that there's a spring-loaded bottom, And right now, the spring is holding the floor of this tank up towards the top. And this is my source. This is my current. This is my pump. And as it begins to pump water or electrons, it comes this way and it falls and it starts to fill up this tank. So as it's doing this, this weight of this water is pushing down that spring, creating more and more tension on that spring as this goes down. The tank's filling and the water that's in there is under pressure because of the spring. And then once it's full and is fully charged, so it's charging a capacitor or charging an accumulator tank. Once it's fully charged, now the water can be delivered to the load. If there's an interruption in the supply to the load can be continued because now this capacitor will release its water under tension and supply the load. Here's what happens when we have rectification. We have these peaks, but if we have a capacitor, the capacitor is going to charge during this time. It's going to fill up. And now on the second half, when this starts to drop down, when the supply starts to drop down, now the capacitor will start to release its stored energy, and you see it showing up here. A small capacitor can only hold a little bit, and it can only release it a little bit. A larger capacitor will release a little more. So you size your capacitor to try to get rid of these pulses. Ideally, you want a straight line. It's pretty hard to get a completely straight line, but with proper filtering, you can get just the very small bumps called the ripple voltage. The ripple voltage can cause problems. It can cause overheating, it can cause noise, it can cause erratic power delivery, so you do get little bumps in your work or your output. Here's a regulator chip that kind of keeps the voltage constant despite fluctuations in the supply voltage. And here is pretty much a complete power supply. You plug it in the wall, puts 120 on the primary. You got your fuse, you got your switch. This represents the core that allows the transmission of primary flux to induce a voltage in the secondary. We're coming in here on the bridge rectifier to the AC inputs, and we're coming out positive and negative DC. I've got a capacitor here that charges up and serves as a supply or reservoir so that those in between those peaks, it can be filled in. I've got a regulator chip that tries to maintain a constant voltage despite any fluctuations that could be occurring over here. I have another capacitor for additional filtering, and at the end, I should have a pretty well conditioned 5-volt DC output. Troubleshooting. Now, I'm going to have you guys think a little bit. Here's the situation. I close the switch, and as soon as I do, this fuse blows. What could be wrong? If you guys are technicians, they're going to call you up and say, man, as soon as I turn that switch on, that fuse blows. What's wrong? And you're the technician, you're supposed to say, oh, I can tell you here in a little bit. Well, let me ask you this. When a fuse blows, what's that typically indicative of? What type of electrical problem?
Overload. Or too much current going through it or something.
Short.
Okay, too much current, probably because of a short. All right, where would that short be that would cause that to happen? We talked about a diode. We said it was N-type and P-type, but there's another type of a semiconductor that's used a lot. I want to talk about that for a little while. And that is a transistor. It has an additional N-type and an additional lead. So no longer is it anode and cathode. It's collector, base, and emitter. Now, it's called collector and emitter because if you look at electrons, the electrons are emitted from this side and collected on this side. But in conventional flow, we're going to assume the opposite direction of flow. Schematic symbol is this. Now here's how this thing works. Current leaves the source, flows into the collector, out the emitter, and into the load. And that's my path. But only if there's base current. This will not work if there's no current going into the base. So I have to close this switch. And if I do, that allows current from this source. Notice this is a small voltage doing this, and this is the large voltage for my load, because this current is considerably 100, 200, 300, 500 times smaller than this current. A little bit of current here controls a big current in the collector emitter. This is the analogy they use with water. You've got a big supply here. I'm controlling the flow, this large flow, with this is in German, but with this little, even could be a trickle, and it's operating a mechanism that causes this flow. You know, inside a transistor, it's not actually a gate, but there's electronic and electrical fields that do control the same output. A little bit of activity here, a little bit of current here causes a very large current to flow on this side. Sometimes you use transistors as on-off devices, switches, transistor switching. But maybe the real value of a transistor is that you can regulate the flow, you can control the flow of emitter collector current. So in that way, this acts a lot more like a valve. You know, we talked about the diode like a check valve. This acts like a regular valve. So if I have this turned way down to where not much current can get through this current is very, very low, then this current also is low. And so the load is operating on low current. It's dim, it's cool, it's slow, whatever the load is. But as I increase the current going into the base, so does the collector emitter current increase. So I can vary my output with a transistor. Think of a, think of a spigot, a valve. I can turn it all the way off and all the way on if I want all or nothing. I can do that real quick, and if I'm doing that, that's essentially switch action. But most of the time when I'm operating a valve, I'm trying to adjust it to get the optimum amount of flow that I need, and that's what's happening whenever I do this. So if I were to sit here and raise and lower this, the current here would raise and lower exactly in unison, but at a much magnified level than what I'm doing over here. So if I'm over here and I'm doing a little bit of movement over here, I'm getting a little bit of movement, or even a slow movement, but it's a lot of current. And if I move this much faster, then this is going to change much faster. It's just that there's so much more current here going to the load than what's actually happening here. This is the basic principle of amplification. I can take a small signal here that I'm creating, in this case manually, by moving a knob, we'll say, up and down, and get a corresponding change that follows my movements, but at a much greater level. That's the principle of amplification. So what I have here is a microphone on the input. This is my voltage source. This is a transducer. I'm taking mechanical energy, sound waves, air, and it's pushing on a diaphragm that causes this coil to move. See the coil moving? That's because the air from the sound waves are pushing it. The waves are like waves. They go up and down. So at one point, this is going in and then it goes out, in and out. It's going positive, negative, depending on which direction it's moving, because in the center is a magnet. So I've got a magnet with magnetic fields. I've got coil of wire that's moving, cutting those lines of magnetic flux. That's inducing a voltage in this coil, and it's being fed out. And it would maybe look like this if you were looking on an oscilloscope. I'm converting mechanical energy to electrical energy. This is a type of a generator. This transducer is a type of generator because I'm converting mechanical energy to electrical. Now, here's a speaker on the output, and it works pretty much like the same thing in opposite. It's got a magnet in the middle right here, and this coil, if it receives current, it's going to become magnetized, and I've got a magnet, electromagnet, and an electromagnet. I'm going to get movement. This is essentially a motor because I've got one magnet, I'm creating another magnet, and that causes them to move. As this is going positive and negative, this is going positive and negative. If this is a little bit of movement, this is a little bit of movement. If it's a big movement, this is a big movement. If this is a slow movement, this is a slow movement. Whatever the input pattern is, whatever the input waveform is that's being converted, this replicates it, but on a much larger scale. This is taking a little bit of air affecting this surface. This is moving a lot of air. Now, here's the thing, air weighs a lot. It's like 14 pounds per square inch at sea level, something like that. So you take something like a 12-inch speaker and a guitar amp. If you do the math of what the area is and then the weight, that's a lot of energy it takes to move that much mass. This microphone does not produce enough power to energize this magnet strong enough to move that air. So it's got to be a strong magnet in order to move with that air pushing down on it. You know, it wants to move. If it were in a vacuum, it would be moving, but with the weight of the air on it, the little bit of current that's coming out of here, because this is millivolts, it's going to take a lot more than that to overcome this air to move this cone. So what do? I use an amplifier. I've got a power supply that pumps larger currents in here, and this varying signal that looks like this is opening this gate up correspondingly, and the collector emitter current follows this pattern, but at a much greater level of current. Now this can't supply this load, but this supply can. So now this supply delivers a large amount of current to this load, but it's being controlled by this small signal. That's how an amplifier works. And you use amplifiers in a lot more than audio applications. You use it in medical equipment where I'm trying to monitor brain waves. Anytime you have something that produces a very small signal, but I want to move things like chart recorder needles and things like that, I've got to get more power to move those kind of things. Amplifiers can do that. This is kind of what transistors look like, their package. This is the analogy. The flow is going from emitter to collector, and the base controls the amount of flow. Now I want to talk about reactants, reactive elements, inductors and capacitors. They're called reactive elements because they react differently in the presence of AC waveforms than they do DC. So DC current has little or no effect on these devices, but AC have profound effects. So when we look at the similarities and the differences. The similarity is that the resistance of these devices from lead to lead, from lead to lead, from lead to lead, the resistance of these devices vary depending upon the frequency of the waveform that's going into it. So here we see waveforms at different frequencies. We see this one's happening at a much higher frequency. There's a lot more of them here in this time frame than down here. This is kind of the middle of the road. high, medium, and low frequency waveforms. How do we calculate the resistance? With this formula. X sub L stands for inductive reactance. This is just a coil of wire. This is just a coil of wire, kind of like a primary on a transformer. Sometimes this is called a choke, and here is the schematic symbol for that. But the resistance, the inductive reactance is calculated by 2 times pi times the frequency times L. L is the quality, the inductance level of this device, and it's determined by other things. You don't have to worry about that at this point. The 2 pi f has to do with 2 pi radians in one cycle. Don't get too caught up on that either, but the f is the important thing, because as you see in this equation, the way that this equation is written in a linear equation, as frequency goes up, so does X sub L. So this resistance, the resistance of this device, goes up as the frequency goes up. What does that mean? It means that if I have a low frequency waveform and it's trying to get into this, it has a much better chance of passing through this device than a high frequency waveform that tends to get blocked. This can block high frequencies and pass low frequencies. The capacitor is the opposite. It's an inverse relationship. This tends to block low frequencies and pass high frequencies. You use these devices in filter circuits. Filter circuits take out things that you don't want and leave what you do want. So if I have a lot of frequencies and I don't want some of them, and some of them I do, I would use filters to do that. Some common application of filters are to eliminate noise, high frequency noise. If we can filter out the high frequencies of noise that's in signals, that helps our signal. The tone controls in your sound system. If I want to have a little more bass, then I'm going to adjust this to let more bass in and maybe block more highs. And you use these in combination, and you use variable devices so that I can make adjustments. Another wide use are tuners, tuning circuits, like in a radio. So let's take a look at that. Here's a long piece of wire. I've got out here electromagnetic radiation coming from the sun, coming from car ignitions, coming from cell phones, microwaves, all kinds of electromagnetic radiation. And as these magnetic lines of flux cut across this piece of wire, it induces a voltage in it. If it's a low frequency, I've got a voltage that's being produced that's low frequency. If it's a high frequency, I've got a voltage being produced as a high frequency. This is kind of acting like a secondary of a transformer. So I've got all these different waves out here. Some of them, most of them I want to filter out, but some of them I want to keep. For example, 93.6 FM. If I can, because it's coming through here too. So radio stations are sending out their signal as electromagnetic radiations at a precise, set, and government regulated frequency. So when you hear about a radio station operating at 93.1 megahertz, so many watts, that means it's sending out magnetic waves at that frequency and that power level. And all of those waves induce voltages. So it's just a big mess. If you were to look at everything that's hitting your antenna, there's just a big mess. So I want to be able to filter out most all of those. So what happens here is all of them come in here, but now I'm only going to, if they're too high, they're not going to get through this thing. So I'm going to size this. I'm going to make these adjustable so I can listen to more than one radio station. But let's just say right now it's set for the radio station we want. All the frequencies, radio stations and noise alike that are below or too high, I'm trying to block most of them. So the rest of them get through. Now that cuts off, that lets my bottom end in, but there's still some that are too high. I trimmed off those, the part of that, but I want to trim off the rest. So now if they're higher than what I want to go, I will short them to ground because this will pass high frequencies down. That only allows that little notch, of frequencies that I wanted to get through. Again, this signal that's being induced into the voltage being induced in this antenna, that's what this piece of wire is, the antenna. This voltage is not have enough power to drive the speaker. So again, I've got an amplifier. The amplifier, we've already learned about power supplies. Here's my primary voltage, my secondary voltage. I'm rectifying it. For simplicity, I just use a half wave rectifier. Ideally, we would have a full wave with filtering and regulation, but you see we've got AC to DC. I've got a DC power supply supplying a lot of current to my speaker, but that current's being regulated by small filtered signal coming from electromagnetic radiation from a radio station. That's all I've got.